So part 2 of this presentation is about testing and engineering design. But first I'm going to let you in on an engineering trade secret. And that every structure that is designed in the country, be it buildings or bridges or towers or whatever that you want, is based on 2 fundamental principles. And that is that materials behave elastically, and the other is that if you apply a force in one direction, there's an equal and opposite force in the other. Elastic material is exactly the same as this elastic band, and the basic concept is there's a linear relationship between the force and the extension. So if I double the force, I double the extension. And if I let it go, it goes back to its original state. And every concept of engineering design makes that assumption, including designing tension structures in both PVC and Shadecloth. But let's start with testing. There are 2 basic types of testing. First, you have uniaxial testing, where the material is stretched in one direction only, and the other, you have biaxial testing, where it is stretched in 2 directions at once. Obviously, in the field, when you are tensioning a structure, it's tensioned in both directions at once, and hence this test is a indication of how it's actually going to happen in the field. But from an engineering perspective, it's important to understand that in this test, the lateral extension is not restrained. In other words, when you pull in this direction, you get contraction in that direction, and that's not constrained in that test. Whereas in this case, it is. So even if you have no load applied in this direction, the fact that the material is held when you stretch it in that changes the elastic characteristics of the material. I mentioned that there is a linear relationship between force and extension, and the relation between that is determined by the slope of the line, which is the elastic modulus, and it's different in that context than it is in that context, and that's a very important thing to understand. If you look at the uniaxial test results, and here we have tests for different colours done at a situation, you can see that the relationship is different first in the weft direction and in the warp direction. Fabric, and this is a tape insert fabric. You can see that it's stronger in the weft direction, much stronger, twice as strong in the weft direction than it is in the warp direction. You can also see that depending on the nature of the test, there is a 20% difference between the best result and the worst result. So again, you're getting this averaging situation, and that the line in this case is approximately linear. In other words, for a uniaxial test, Hooke's law, that is, force is proportional to extension, applies. So in other words, if you double the load, you double the elongation. Basic principle. Now let's look at biaxial test results. The diagram on the left here is the load diagram. It shows that the fabric stress occurring in the warp and weft direction at the same time. In other words, the loading is the same, and over time you go up and down as you increase the load and decrease it. The strain diagram on the left shows that, and you will note here at the first cycle in the warp direction is almost linear, but the next cycle it behaves very, very different. You have a very significant stretch set in that direction on the first cycle, and you also have a significant stretch set in the weft direction. But the other thing to notice is that the strain in this direction is so much that it's inducing strain in the opposite direction, which is causing a negative strain. In other words, it's still contracting even though it's being pulled out with the same degree of force shown here. And this is more obvious if you superimpose the uniaxial results on the diagram. You can see the slope of the uniaxial line is approximately the same as the biaxial line in that context. But here, in the biaxial test, the fabric has become much stiffer as it turns. In other words, the elastic modulus changes very significantly. So for this particular fabric, it hasn't changed very much in the warp direction, but it has changed significantly. And the significance of that is you are getting a lot of extension in the warp direction as you pull, and you're still getting contraction in the weft direction, even though you are pulling with the same degree of force in each direction. And that's the nature of how these fabrics behave. You also have a thing called creep. Now creep is, and this is a picture of the test apparatus here, and you can see that you've got a load here, which is approximately 0.25 kilonewtons per metre, and a strain gauge measuring over time the elongation. And you can see clearly in this diagram the lateral contraction being caused by the load in this direction. You see how the fabric in fact is curved inwards like that, which is showing the maximum strain in the middle there in the opposite direction to the force being applied. But the thing to note about this is that at time zero here, there is no response of the fabric, and it takes an hour for it to actually respond to that degree of loading, and continues over a period of time to relax. In other words, the extension of the 24 hours is 1.8%, or average say about 1.5% in that direction after 24 hours, even though the original extension was zero. And that behaviour is displayed in both warp and weft direction to a different degree. Now this has a pretty significant impact on when you are tensioning in the field. You have to recognise that you are going to get continued reaction to the force applied when you tension the fabric. So how are these parameters derived? Well, there are a number of publications that show you how to do that. One in the US, this one, tensile membrane structures, and you have the European Design Guide. They give you ways of doing it, and in fact, the biaxial tests have to be done in a certain way to allow these procedures to be done. If we look at the outcome here for a typical result for a 240 GSM monofilament and tape, the first line here, you've got the approximation. These straight lines here, here and here are the approximation to the biaxial results, which is shown dotted there. The blue is in the warp direction and the red is in the weft direction. And you can see that the theoretical approximation of that behaviour is not bad in that context, but in actual fact it's really nothing like how the fabric behaves in practice because of the stiffening that occurs on the second cycle. In other words, although we've assumed it to be elastic, it's not. It's not behaving in elastic fashion. This first line, and I'm sorry to get a bit technical here. First line here is the uniaxial case, and the stress is equal to the elastic, unrestrained elastic modulus times the strain. Second line here is where the fabric is restrained, like it is in a biaxial test. And again, you've got the same thing, but this elastic modulus is not the same as that one, because this is for the unhindered situation and that's for the hindered situation. That is uniaxial test and biaxial test. And if we look at final situation for Hooke's law, which relates the strain in both directions, that is in the weft and in the warp, that value of the hindered elastic modulus times the strain in the warp direction, and this third modulus, which is the stiffness matrix between the two directions, times the strain in the weft direction. And you can see that equation, which is what engineers use to model this, is pretty good. Matches that initial slope. And considering that the forces that you are using is in this part of the diagram anyway, this is the very much at this bottom end. The actual elastic theory gives a pretty good approximation. Finally, we have the relationship between geometry and applied loads. Now this is useful for determining logically the process for setting out. And if you look at that particular diagram, which is supposed to be a plan of a high-pass structure, similar high-pass structure, and you look at the chord, the loading in the chord, the depth of the chord, the length, the radius of curvature, all of these things can be related with fairly simple equations. So the depth there, the chord length, can be shown, can equal that. So you can calculate for the allowable tension in the cable, the design stress, and the length between the thing, what the finished chord depth would be. So and this can be approximated by that equation, and hence you can derive a relationship between each of these particular depths using that expression there. And you can get the arc and cable lengths using that expression. So if you've got a design structure and you're starting off with a chord depth that you might estimate, you can work out, given the change in the cable length due to the tension that you are applying in it, which can be got from the various tables, you can estimate where you're starting from and where you are going to finish using these formulas. Now, all that's great theory, but in actual fact, a lot of fabricators just use experience. But there are a couple of key features to understand. First is that the maximum stress is due to wind load, and that generally occurs in a high-pass structure along the axis of the low points. And it makes sense then to align the fabric in the strongest direction, which is the weft direction, like that. So the fabric is aligned along the axis of the low points, so that the weft is aligned in this direction and the warp is aligned in that direction. Now what that means is that each of these curves is then cut at a 45-degree angle, so that even though the elongation characteristics are different in each direction, because it's 45 degrees, it's the same. And because the cable here, if it's continuous, it exercises constant tension, then the deflection in each of those directions will behave similarly. Generally, experience shows, in Australia anyway, that you should allow a 4% contraction in the warp direction and a 2% contraction in the weft. Now, all of this stuff, all these formulas are shown in technical manuals. The derivation is shown in the appendix, and also the most recent update, which is still in preparation, provides the information that supports all those formulas and also the method of calculation. So thank you. Any questions? If not, come and visit Sydney if you haven't done so already.